Hi students, Professor Gray here. Apparently I recorded this video with no audio and I don't know how that happened, so here I am recording it for you guys again, which is kind of a pain, but oh well, that's what happens sometimes. So let's get going on this. Molecular structures. So on this slide, we've got a couple of molecules, ethanol and dimethyl ether. Now, if we take a look at this right here, their molecular formula, you can see that the molecular formula is C2H6O for both of them. And that seems really strange. But if we look over at the structural formula over here, we can see that the carbons and the 6 hydrogens and the oxygens in these molecules are connected differently. And that's called atom connectivity. So they have a different order of atoms, and the atoms are bonded to each other differently. And this is okay, this happens. These are called isomers. And isomers are molecules that have the same chemical formula, but they have different atom connectivity, so they have different chemical structures. Now the molecular formula over here, the C2H6O, that gives us the number of each of the atoms in our molecule, but it doesn't give us any hint to the structure of the molecule. And if we look at the structural formula, it shows us how the different atoms are connected and what kind of bonds we have in those atoms. So both of these molecules, ethanol and dimethyl ether, they have only single bonds. Now, if we want to do a shorthand for the structural formula, because sometimes that's kind of awkward to put in a book or on a piece of paper when you're in a little bit of a hurry or you just don't want to draw all of that out. So what we can do is a combination of the molecular formula and the structural formula, which is the condensed formula. So you can see how that saves a whole lot of space compared to the structural formula. Now the condensed formula is going to have the same number of carbons and hydrogens and oxygens as the molecular formula, but it's going to arrange it in a way that gives you a hint as to the structural formula. So if we look at this first part of it, the condensed formula says CH3. Now that doesn't mean that we have a carbon bonded to 3 hydrogens in a row and then another carbon and 2 hydrogens and an oxygen and a hydrogen, because that would be completely different from this over here. And what this is saying to you is you have a CH3 unit on the end, which is right here. And then you have a CH2 unit, which is right here. And then you have an OH, and the OH shows up right there. And for dimethyl ether down here, you can see again that you have a CH3 unit on the end, which is right there. And then you have your oxygen, and then you have another CH3 unit. So again, you don't have carbon and then 3 hydrogens in a row. You have a carbon bonded to 3 hydrogens, and then an oxygen, and then another CH3 unit. And another way that you guys will see molecules represented is the ball and stick model and the space filling model. And on this slide back here, you can see that you've got the two combined. So the ball and stick model, it shows up in the center there, and then the space filling model is kind of behind it a little bit. And what we'll notice about the ball and stick model is that you can see all of the bonds and all of the atoms clearly. The problem with this is that the size of the atoms and the size of the bonds are not proportional to reality. Here we have bonds that are a lot bigger compared to the atoms in these models than they would be in reality. Now, the space-filling models, that shows the relative sizes of the atoms to each other a whole lot better. But the problem with these ones is that you can't see behind the molecules. You can't see what's back there. Now, a lot of the new software will let you turn this molecule around, but I can't do that right here. So we'll just have to be okay with the fact that the ball and stick model allows us to see all the atoms and all the bonds, but the space-filling model gives better perspective to the sizes. If we take a look at ethanol, on the left is a ball and stick model that you would put together in the classroom if we could go to the classroom right now. And on the right is the space-filling model. And you can see clearly that you can't really see what's behind there. Now, with our models, usually the carbons are black and oxygens are red and the whites are hydrogens. The other atoms have different colors depending on which model kit we use and what your favorite colors are. So the next slide shows the special molecule called benzene. Now, benzene has a formula C6H6. And if we didn't have all of these drawings around benzene right here, it might be a little bit difficult for us to figure out what is the structure of benzene. But over here to the side, fortunately, we have it drawn already for us, and we can see that those carbons are in a ring. So you've got a 6-membered ring, and you have an alternation of double and single bonds all the way around the ring. So you have double, single, double all the way around. And each carbon has one hydrogen on it. Now, if we look down here, we have another representation of benzene. And what this model does for us is it saves us time. We don't have to write any of the carbons in, but it assumes that you know a whole lot more than you know at this point. Now, if you guys go on to take organic chemistry, what you'll learn is that at every point on one of these structures, we assume that you know that there's a carbon there. We also assume that you know that each carbon likes to have 4 bonding pairs around it. And we'll learn that in the next few slides when we learn how to do Lewis dot structures for entire molecules. So if we're taking a look at the top carbon, you can see that we've got 1 bonding pair here. We've got our second bonding pair here. And remember, every single bond is 2 electrons, and that means that a double bond is 4 electrons, so we've got 2 bonding pairs in that double bond right there for a total of 3 bonding pairs if we count all of the blue lines. And so that means that that carbon on the top there only has 6 electrons around it for bonding right now, and that's a sextet, and that doesn't make that carbon happy. It needs to have 8 because it wants to have an octet, which is something that we've heard before. So then we know that that carbon has to be bonded to something else. And in organic chemistry, what we know is that carbons love to bond to hydrogen. So we just assume that there's a hydrogen there whenever we need to bond a carbon to something else. And then that is true for all of these carbons all the way around the ring. And now you can see that's exactly the same as this structure up here. So that brings us to this guy right here, which is also a representation of benzene. And it's another way that you guys will see benzene drawn. And the reason that we have the ring in the center is because the double bonds in the benzene ring actually don't stay in place. they're not localized, which means they're not stuck there. They actually flip around like this. So what you get is a spinning around of those electrons right there. And that's why we draw benzene with that circle in it sometimes. So all three of these right here are different molecular structures for benzene, and here you have the molecular formula. Now down here we have a space filling model, and that looks like a lovely pillow that you might throw on the floor and jump on and watch some TV. So that looks like a nice squishy molecule right there. But benzene is not a very nice molecule. It's cancer causing, so we really won't want to be around benzene too much. And now I'm going to stop this video just to make sure I've got audio on it this time and upload it, and then we're going to go on to Lewis dot structures.